Hi everyone. Today we're going to continue with the 2D systems. Let me say about your exercise number 3, that it will be due 2 weeks from now. Okay? Because it'll take us some time to cover this material, and then we should finish the material for exercise 3 next week, and then you'll have a week to finish the exercise. So last time we saw the different types of fixed points that we can have in the 2D systems, and we also discussed 2 definitions for stability that are finer than stable versus half stable. That was attracting or non-attracting, and then Lyapunov stable or non-Lyapunov stable. Today we move on to show the general solution for the linear 2D system. It's not complicated, but it makes use of basic linear algebra, and I understood that some of you did not learn about eigenvalues and eigenvectors yet. Is that right? You did not. Eigenvalues is something you're not familiar with. Okay.
Probably like this week or next week.
Okay. So I'll try to explain things as I present them. But yeah. Okay, so remember that our system has the change in the vector x, which is actually coordinates in the 2-dimensional plane. So the change with time of the vector x is described by a matrix A acting on the vector x, multiplying it from the left. Okay? Now, this is a differential equation, right? And it is possible to write a solution for it. So I'm going to present the solution, and then as we do with differential equation, we kind of guess a solution sometimes, and then we substitute it to see that the equation is satisfied. So the solution to, first, we're already encountering the eigenvalues, and so I'll just present briefly eigenvalues and eigenvectors. Okay, so very generally, if you have a matrix like our matrix A acting on some vector, okay, A times x, it is possible that multiplying this vector by the matrix will give you some scaling of this vector. Okay, just in each position, in position 1 you'll get back x, in position 2 you'll get back y, but they will both be scaled by the same factor. So multiplying by this matrix is equivalent to multiplying the vector by some scalar. Okay? And when you have that, this special value is called the eigenvalue. It comes from a German word, eigen, meaning self. Okay, so it's the self value of the matrix. And if this happens, if the vector can be multiplied by the matrix to give the same vector times a scalar, the eigenvalue, then this vector is called an eigenvector. So a matrix can have several eigenvectors, these vectors that are very special with relation to this matrix, and their property is that when you multiply them by the matrix, you get back the same eigenvector, only multiplied by a certain number of by a certain scalar. And well, you'll see in Yoav's lesson how you determine how many eigenvalues there are and what it means, whether a two-dimensional matrix has two eigenvectors and two eigenvalues, or one eigenvalue alone, or so on. And in this lesson, I will show a method of finding, for a matrix A, finding the eigenvalues first, and from them the eigenvectors. Now, this is not my specialty, so I'm not sure I'm doing a good job of presenting this topic, okay? I trust that Yoav will do a better job than me. So whatever he says, listen to him, okay? Okay. So I'm telling you that the solution to this system is of the form, there is a solution of the form x equals an exponent of lambda t times some vector, where lambda is an eigenvector, eigenvalue of A, and V is some eigenvector of A. So I'm telling you that this is a solution. And now, in order to see whether I'm telling the truth, what we need to do is to substitute the solution in our differential equation. It's possible that eigenvalue and eigenvector should be written with a lowercase e, but the Germans would write it with a capital E, of course. Yeah.
If there are few eigenvalues, then you have to.
Okay, yeah, I'll get to that. Okay, but I'm telling you that this is a solution.
Okay.
It's not the solution. Okay? So when I substitute it, okay, I'm going to take the time derivative of this and this should be equal to the to A times my solution. So the eigenvector is just a vector. Okay, it's an xy coordinate. It doesn't change with time. So all I need is to differentiate the exponent. What I get is lambda times e to the lambda t, and the eigenvector remains unchanged. And then the exponent times lambda t is just a scalar. Okay? For any t, this will be a scalar, not a vector. So I can put it here to the left of the product. So I'm still asking whether these are equal. Okay, and A times the eigenvector is, of course, lambda times the eigenvector. The eigenvalue for this eigenvector times the eigenvector. So this is indeed equal to this. So this is a solution. And we call it an eigensolution. what I did here?
Yeah. So you're taking the derivative of fa.
Yes.
Okay, and you get that back again. Or you get.
You get the lambda
Yeah.
preceding everything. Okay. And then you have, okay, you get lambda preceding everything. And here, this is a scalar. Okay, it's unaffected by the multiplication by the matrix. So the scalar can be brought out, and then you remain with the matrix times the eigenvector. And since this is an eigenvector of the matrix, this gives you the eigenvalue times the eigenvector. Now, I don't know yet what?
So what have we proved?
That the solution that I proposed is indeed a solution. This was a kind of
It's a solution
to this.
Okay.
Okay? I just proposed this, and then I checked, and it turned out to be a solution. And I don't know in advance the eigenvector and the eigenvalue. Okay, so this is a general form. I'm saying if there is an eigenvalue and a corresponding eigenvector, then this will be a solution for the system. Okay? And now, this was supposed to be a reminder, but some of you have not seen this before. The next thing I want to do is to find the exact solution. Okay? I told you a general eigensolution. It had lambda and it had v, which I did not know. So now I want to calculate lambda and v. Right? So what we do is basically we start from this equality. Okay, this is the definition of the eigenvector and eigenvalue for A. This is what they basically satisfy, right? And I want to subtract this from both sides. So A times V minus lambda V. What I remain with here is just the zero vector. And then this can be written, okay, times V minus lambda times the identity matrix, right? Identity matrix. If this multiplies a vector, you get back the same vector. Okay? Right. So I could just put this in here. Right. And then I'm going to write this as A minus lambda I times V, and this should equal the zero vector. And then this equation means that this is a new matrix, right? So if I had A equals A, B, C, D, now I have a new matrix, A minus lambda I, which is A minus lambda. Here I have B, here I have C, here I have D minus lambda. This is a new matrix, which is now multiplying V from the left. So if this matrix is multiplying V and I'm getting back the zero vector, this means that the determinant of this matrix must be 0. And this is what I'm going to use in order to find the eigenvalues. Okay, you already know how to find determinants, right? Yeah. So I'm using this condition, which is equivalent to having this equality. So, okay, the determinant of A minus lambda I equals determinant of, okay, okay, so first I multiply these two. Then you need to subtract the product of this diagonal. I'm going to open this, so I get AD minus lambda D minus A lambda plus lambda square minus BC. Okay, remember our condition will be that this is all 0. Okay? So when I demand that this is 0, I get a quadratic equation on lambda. And I want to find the lambdas that fulfill this. Remember, I'm finding the eigenvalues of the matrix A. So, okay, so I'll write this again as I'll group the different orders. Sorry. Okay. Now I got the quadratic equation as I like to write it, and I want you to notice that what I have here. Okay, this is trace A. A plus B is the trace of A. And what I have here is the determinant of A. Okay? So basically, my quadratic equation looks like this. Minus, okay, I use a shorthand. I write trace as tau and the determinant as delta. Okay, and by the quadratic formula, I might have two solutions for this equation, right? It's a parabola. Here you should have minus the first order term, but that was minus trace, so you just have plus trace. And these are the eigenvalues of the matrix for any matrix A that you get. And you can already see that if this difference is 0, you'll only get one eigenvalue for this matrix. Okay? And if what's written here is negative, you're going to get complex eigenvalues. And this is okay. Remember, our variables and all these parameters that we have are real, but it's possible for the eigenvalues and eigenvectors to be complex. Okay, so these are my eigenvalues. And as you can see, their values and their existence and their being whether they are real or complex depends on the properties of A, and especially on the trace and the determinant. So instead of referring all the time to A and its 4 parameters, we can deal only with the trace and the determinant of A. Okay, so now I would like to find the eigenvectors. And the eigenvectors satisfy each eigenvector should have, in the general case, should have its own corresponding eigenvalue, and they fulfill this equation. And okay, so if we have two eigenvectors, of course, this will look like this. And then what we do is okay, we don't know the eigenvectors, so we just call its two components by names, say UW, and then we should write explicitly the equation A times UW for the system of equations. So you should write this whole matrix and write explicitly the multiplication and solve the two equations, or actually one of them. We'll do this in an example later. And I think by the end of the lesson, you'll see an example of exactly how to find the eigenvector. Okay, I move on to looking at the different cases that I may have, or yeah. Okay, we start from the typical case where we have two eigenvalues that are different from each other. Okay, and in such a case, we also have two eigenvectors. And when you have two eigenvalues and two eigenvectors, then the eigenvalues, they're linearly independent of each other, and they should span the whole plane, the whole two-dimensional plane. What? The eigenvectors, sorry. Yeah, the eigenvectors span the two-dimensional plane. And if they span the two-dimensional plane, then any initial condition that we have for the system can be written as a linear combination of these two eigenvectors. So linear combination with corresponding coefficients C1 and C2, right? And then remember, I told you that this is a solution. And this should be true for any eigenvector of the system, right? So basically, if I have two eigenvectors, I have two solutions. I have this for lambda 1 and v1, and this for lambda 2 and v2. And since my initial condition has components of these two, then the general solution for any initial condition should also be a linear combination of these two solutions, v1. And what this means is that our system is basically living in the system of coordinates of these two eigenvectors. Okay, so it is evolving independently on each direction, or maybe in order to make this more concrete, we may have two eigenvectors, okay, v1 and v2. So these are two directions on which the system is evolving independently of the other direction. And so if my x0, say my x0 is just a linear combination, right? So this will be x0. Linear combination of these two. What will happen to it, then on this direction, it will evolve according to lambda 2. Okay, just exponential growth or decay along this direction. And on this direction, it will evolve according to lambda 1, either exponential growth or exponential decay. So this is like decoupling the system, or writing it in a relevant system of coordinates. Yeah?
Can you explain the transition between x0 and xt?
Yeah. Okay, so I know that this is a solution. So if I feed the system with V1, for example, what will happen is that it will evolve according to this. This will be the function with time. And if I feed the system with V2, it will evolve according to this, but lambda 2 and V2. And so if I feed the system with a linear combination of them, and they are linearly independent, then the system will evolve according to this with a prefactor C1, according to the original combination, and plus this with a prefactor C2. Okay? So this meant that the system evolves independently for each eigenvector. Yes?
So and when you have this is a solution to the system, so that means that it's a solution for a particular x0, right? Is that what you mean?
This one?
Solution? Or in other words, for each eigenvalue that
Yeah.
you get, you have a solution for a particular x0.
For each, yeah, this particular x0 is the corresponding eigenvector. Okay? So I'm saying
It only tells you about the system at those two x0s. It doesn't tell
exactly
you
at
about the system
here and here. Yes, but I'm telling you, and Yoav will teach this more in depth, that if you have two different eigenvalues, then these are linearly independent, and they span the plane. So each point on the plane, each initial condition, can be written as a linear combination of these two. So, as you said, my guess gave me these two. Okay. But any point here can be written as a combination of them.
But you don't know that that's a solution.
This?
That form is a solution for other x0s.
This one?
Yeah.
Well, what I would do is take all this and put it here, and then I will find that it is a solution. This is how you check that, and you're welcome to do it later. Yes.
You said that these eigenvectors are independent, and they
Yeah.
are the direction in which the system goes independently.
Yes.
Every basis that I will take,
Mm-hmm.
the standard basis also is linearly independent.
Yes, but
so why this is different?
yeah, the system does not evolve independently on them both because they are independent. Okay. It evolves because they are eigenvectors of A. So this is a special base for the plane.
Why special?
Because it is the eigenvectors of A. So the normal base, okay, 1, 0, and 0, 1, it's not it's not the eigenvectors of A.
No, I know, but
okay.
Why the eigenvectors are special? This is the question.
Why are they special? Because when you feed A with the eigenvector, you get this, okay? Okay, and this is like saying x, y equals lambda x equals lambda y, okay? And then the solution to this is x equals x0 e to the lambda t, and y equals y0 e to the lambda t. So when x Okay, when X is an eigenvector, yeah, let's call it, when X is an eigenvector, so in fact we have, yeah, X equals AX, and we are saying equals, say, lambda 1 X, and X is an eigenvector, right? So X is, in fact, is the initial condition. So my x0 equals v1 equals uw, right? So what I have here is like saying that xy equals lambda 1 xy, and not only not xy but uw. No, wait a minute. Oh no, xy equals lambda 1 xy, and my initial condition is this, okay? And then x equals lambda 1 x, y equals lambda, dot lambda 1 y. Yeah, like I wrote here, only that x0 is u and y0 is w. Using the eigenvectors means that the system is decoupled, that it is basically two uncoupled equations. So x is evolving on its own and y is evolving on its own. Okay?
Can just look at it only in the x direction for the system?
Yeah.
And see the
Well, not the x direction.
and the eigenvalue.
Sorry, it's not x that's evolving on its own. It's the first eigenvector that's evolving on its own. If you look on that, and then it will just be growth or decay.
And no change in the other direction.
There might be change in the other direction, but you need to look at the second eigenvector for that.
Yeah, but in the direction of the first eigenvector, there will be no change in the second.
Well, yeah, because now you are working in the base of the eigenvectors, so you don't care. I mean, your new base is only going on one eigenvector or going on the second. So even if they're not orthogonal, they don't need to be orthogonal. Okay. So, as I was saying before, this is a solution, okay, because it's a linear combination of solutions. And this comes from differential equations, where always, if you can find different solutions that are independent of each other, then the general solution should be a linear combination of these two. And you can check that this is a solution if you plug it into the equation, right? And since this solution satisfies, okay, that at time 0 it is at x0, then it is also the only solution. And this comes from a theorem called the existence and uniqueness theorem. Which we do not learn. You can see it in the book, but we will see it later when we really need it. But what it says is that if there is a solution for the system for a certain initial condition, then it is the only solution. Okay, so this general case of lambda 1 and different from lambda 2, I would like to ask, what does it look like? Okay? And then we need to start considering whether lambda 1 and lambda 2 are negative or positive. Okay, so say lambda 1 and lambda 2 are different, and one is positive and one is negative. So we have our system, and it should have two eigenvectors, v1 and v2, and then on lambda 1 we have growth, right? Because the solution corresponding to lambda 1 would be e lambda 1 t v1, and lambda 1 is positive. So already on the direction of v1, I will mark arrows going out from the origin. Remember, the origin is a fixed point, always in this type of linear systems, which are homogeneous. And on the direction of lambda 2, we have decay. Okay. So I'm marking the vectors. Their arrows point outwards, but the trajectories, the flow of the system can point in another direction according to lambda. So this is when you are on an eigendirection. If you start here, for example, you are expected to flow to the origin, okay, because you have a strong v2 component. But you also have a v1 component that always grows. So your trajectory will look like this. And similarly from here, and from here, and from here, you go in along v1, and you go along v2, and you go out along v1. And this is a saddle point. So I leave it empty, okay, because it's according to our notation, it is an unstable point. It should be empty. And we saw the saddle previously, right, when our eigendirections were just the x and y axes. So this is a saddle that is kind of tilted and stretched, because now we are talking about the eigenvectors. And this will always be true. If lambda 1 is positive and lambda 2 is negative, you have a saddle.
Does this have a correlate in one dimension, or does the notion of...
No. Okay, now say that both lambda 1 and lambda 2 are positive. Now I have my eigenvectors v1, v2, and I have growth on both of them. Okay, so I start drawing the system by drawing what happens on the eigendirections. Have growth along the eigendirections. This is clearly an unstable fixed point. Unstable fixed point. And what happens here, Okay, so we will have one of the lambdas larger than the other. So say lambda 1 is larger than lambda 2. So the growth along V1 should be faster. Okay, what I get is this. See that eventually the trajectories align more strongly with V1 because it is more dominant. And as the component of V1 gets bigger, it becomes even more dominant. Its growth becomes even bigger compared to V2's. And this is a type of consideration that you are expected to know how to do yourself. Okay, lambda 1 is bigger than lambda 2, so the trajectories should go eventually to the direction of V1. Now, say they are both. Yeah.
We had the saddle point there.
Yeah.
And here we don't have a special name for it.
It's unstable fixed point, and you can call it a node. It's a node, and it's an unstable node. But later, we'll see that a node is a general term, and we will see finer distinctions of different nodes. Okay, now what should I draw here? Both eigenvalues negative, going in, right, along both eigen directions. Now say lambda 1 is so lambda 1 has is more negative. This is a faster decay than lambda 2, okay? So similar to what we have before, the decay on lambda 1 is faster, and so we have this same shape, only with the arrows pointing in a different direction. This is because if I start here, for example, my fastest decay is along V1. So first I decay very fast along V1, and I am approaching V2, and only when the V1 component has become very small, now the decay on V2 is becoming more apparent. Okay, and you can draw as many arrows as you want. This, and it's a kind of spider shape. And this is a stable fixed point. We call it a node. And we mark it with a filled circle. So, okay, we'll see later what exactly is called a node and what is and what special cases are not called a node. Okay. Okay, now we take a break. according to that clock, which is it's not correct, but until 2:05 according to that clock.
ראית כמו שחייך היום, ראיתי יש לי הערות של עיקרון וכתיבה בעברית ולא הסכמתי אותה בדרגית 2 פשוט כי אני לומד במחקר מאוד גדול.
כן, זה ברור.
להבא אני...
בסדר, כתבתי גם...
כן.
גם לא הבאתם את זה.
כן, כן, לא.
לא הבנתי.
כן, אני... אתה יודע, יש לי מלא דברים לעשות אם אני לא... קיצור, לא נותן לעצמי ככה...
לא, אוקיי.
וגם כאילו שזה יהיה... אתה פה. אני יכולה להתחיל לעצמי ולחשוב שלך. אני אגיד לך, אני יודעת שאני מתכננת, אבל... ולא יהיה לי מושל לזה, אז אני אחריק את זה. ולא כדאי.
כן, זה לא קשה...
גם אם אני לא אעשה כמה בדרך, אז אני לא באמת אתקדם. זה לא...
לא כל כך הבנתי פה איך רואים לפי הציור של V1 מושך את זה V2.
כי כשאתה נמצא רחוק מנקודת השבט, מפה, הכיוון הוא
בעיקר על V1. בעיקר ככה זה לפחות. בעיקר מקביל ל-V1 ולא... אבל נגיד אם אתה מתחיל מפה, אז הכיוון כן. אם אתה מתחיל מפה, לפי V1 שלך הוא מאוד קטן. אוקיי. נניח שהוא קטן מ-1. ואז השינוי ל-dt על כיוון V1 יהיה... הוא יהיה כאילו... הרי אם יש לך איזשהו x ואתה קטן מ-1, הפונקציה האקספוננציאלית היא יותר נוחה, כלומר יותר קטנה, השינוי אפילו עוד יותר קטן. וממש הרכיב של V2 יהיה גדול, אז באמת כאילו תלך יחסית למקביל ל-V2. אז כאילו לפי מה שאמרתי מהציור הזה זה שהקווים תמיד חוצים את הקו של V1 והם סוג של כאילו ככל ש-V2 יותר גדול אז הם ישיקו לו יותר. נכון, כן. במין משהו כזה, אבל אף פעם לא חוצים אותו. הם תמיד חוצים את V1
לא, הם לא חוצים רק אחד, הם רק חוצים...
הם מגיעים לפה כי אתה... כן, זה נראה כאילו... זה היה כאילו מצוין בין פרבולה כזאת שהולכת...
לא, כולם מתחילים...
כן, לא, תגיד שאמרת באמת היה באותה נקודה.
לא, ממש באותה נקודה.
Okay. I've elegantly ignored the option of lambda 1 and lambda 2 being complex numbers. Okay. We'll look at that now. Okay, so remember we had lambda 1, 2 equals tau plus minus square root, tau square minus 4 delta, everything divided by 2. So if we have tau square minus 4 delta negative, then we get two complex eigenvalues, which we will write in the most general form as alpha plus minus I omega, where alpha is the real part, and they both have the same real part, right? Tau over 2. And omega is a complex part. So our general solution still holds, only now our eigenvalues are complex. Our eigenvectors are also complex. And our, okay, so V1, V2 are complex. And the coefficients are also complex. So your x0 is, of course, real. You must be able to locate it on the xy plane. So x0 is real, but it's written as a combination of complex numbers and vectors. Okay, so what does it mean? What does the system behave like when we have complex eigenvalues and eigenvectors? So our general solution, okay, let's say that I use the Euler notation to write Ci. Let's write Cj equals Rj e to the I times rho. Yes. Yeah. And Cj Okay. What? Cj is the j component, okay, 1 or 2. So I'm just writing it as a complex number. I'm writing each component in the vector v1, for example, as a complex number. So vj v1x is m1x times e to the I mu 1x times, sorry, not t, without a t. This is not dependent on time. And I have my lambdas. Okay? So now if I want to write my general solution, C1 e to the lambda 1 t v1, C2 e to the lambda 2 t v2. And then I have Okay, R1 e to the power of I rho 1 e. In the power I have alpha plus I omega t, like this. And then I have V1, okay, where I will have M1x, M1y, e to the I mu 1x, e to the I mu 1y, okay, and so on. 2e. This is minus here, minus omega t, and then m2x, m2y, and this will be my general solution. And I can also write it in the regular form of real plus, okay, break down this to real and imaginary parts. But what's happening here is that this thing,
Can you write this a bit larger,
yeah,
and make it on top of the E?
yeah. Okay, it doesn't matter much. Like this. What I do with this is I break this down into e times alpha t, e to the alpha t, times e to the I omega t, right? So this is a real coefficient that is it might be growing or decaying with time, right? And this is a complex number, and it's basically the way you write it when you separate its real and imaginary parts is this. So what the system is doing along the first eigen direction is growing or decaying according to the value of alpha and oscillating according to the value of omega. And now you see why I called it omega. It's the radial velocity. Or, sorry, it's not the radial velocity, it's the frequency. The radial frequency. Yeah, radial velocity is okay. So we have growth or decay with oscillations. And the same thing is going to happen here. Because if we take this, we have cosine of minus omega t, and the cosine of the minus is just the cosine.
Why is it minus over there?
Here, this is the second eigenvalue. It's a complex conjugate of the first. So on the second eigendirection, we have growth or decay according to the same alpha. Okay. And then we have oscillations according to the same omega. And you can see, well, our x, okay, x is the sum of all this. It should be real. So all the complex, all the imaginary numbers that come out here, for example, this one and this one, they should be canceling out eventually. Okay, and you should get no imaginary parts in x. So what we care about is only the real parts. Although, okay.
Can you explain once again what cancels?
All the imaginary things that will come out, for example, from here you have an imaginary component. From here you have an imaginary component. And also here. And here, and here, and here. So when you do all the multiplications and additions and subtraction, you should be left with nothing imaginary. Okay? So this doesn't mean that these will not be seen in the general solutions, because they might be multiplied by another imaginary thing. Okay, and then we'll get I times I, and it comes back as real. But the general behavior here is growth or decay with oscillations. And this is what we call a spiral. So if the real part of lambda 1, which is equal to the real part of lambda 2, if it is negative, then we'll have decay. Okay? You can have several such trajectories. And this is a stable. It's a stable node with complex eigenvalues. So we call it a stable spiral. We reserve the term nodes for fixed points with no complex eigenvalues.
Say the real part, you mean the e to the power and the cosine?
No, I mean alpha.
Just, okay.
It's alpha.
So,
Yeah.
when you, why did you have to assume that the real parts of lambda 1 and lambda 2 are smaller than the 0?
No, I did not assume. I just said that in this case, everything is decaying.
So it's stable.
Yeah. So, and you can imagine that you have oscillations on x and on y. Here we cannot draw the eigenvectors because they are complex. Okay.
Is there a general form? You said that the imaginary values disappear. So is there a general form for what happens? I mean, once that happens, that it's just. What will be the answer after you do all of this and you get an equation?
Yeah, you can write it down. I have part of the answer here, but I won't go into it.
Okay, but there is, in other words, there's a general form for a given that you have.
Yeah, you can reach a general form.
Okay.
It's not very interesting. Okay. Yeah.
If both of them are decaying slow, it's a stable spiral, and if both of them are growing, it's an unstable spiral.
Unstable spiral. No, you can't have that.
You can't have that. Okay.
Because you have a single alpha. Okay, so we are now going to look at a systematic way of classifying fixed points for linear two-dimensional systems. And we saw already that the type of fixed point depends on both eigenvalues, right? And I'd like you to note that the trace of the matrix is the sum of eigenvalues, and the determinant is their product. Okay? If I add lambda 1 and lambda 2, the square roots will cancel. I'll get half tau plus half tau. I'll get the trace. This is if I add the two eigenvalues. If I multiply, then I will get back delta. Okay? You can try doing that, right? This is lambda 1 times lambda 2 equals 1/2 trace plus square root square minus 4 delta times 1/2 trace minus equals 1/4 trace squared minus what you have in the square root. This cancels. Plus. Wait a minute. Where do I get the plus from? What?
Minus. Look at the parentheses.
Plus 4? Oh, yeah. Right. Sorry. Yes. So this is delta. Okay, so already we can translate what we found before to conditions on the trace and determinant. So if both lambda 1 and lambda 2 are positive, then you have a positive trace and a positive determinant. If they are both negative, you have a negative trace and a positive determinant. And if they are unequal sign, you get a negative determinant, but you don't know about the trace. Okay? And remember, this was the case of an unstable fixed point. This was a stable fixed point. And this was a saddle. Okay, so I want you to make room for this plot. We are going to plot the plane of delta versus tau. So each point on this plane is a system. It's a possible linear 2D system. And now we are going to divide the plane into the different types of fixed points. So let's start with this. Delta smaller than 0. So, excuse me? So all of this half of the plane will be saddle points. Okay? It doesn't matter what the trace is. And I can make a small drawing. X, Y. Now, for positive delta, a positive tau gives you unstable fixed points. We'll write unstable nodes. A negative tau gives you stable nodes. And we already had a condition here, right? This condition, or I like to write it this way. That gives us the spiral. If this is met, then we have a spiral in our origin of axes. So trace square over 4 is a parabola. Here. Trace square over 4. Stable nodes. So above this parabola, we should have spirals. If the trace is negative, then alpha is negative, and we have stable spirals. If the trace is positive, we have unstable spirals. So strictly, a node, a spiral is also a node. But in this, so you can say that this is a spiral and this is a regular node. But in this course, we will use the term node for things that are not spirals. Okay, now we will look at some special cases. First of all, what happens when alpha is equal to 0? So this means the trace is equal to 0. And we are on this axis here. So we're talking about the case where this condition is met and the trace is 0. So delta can be any delta, but we are on this axis. So this means we have no growth or decay. Okay? This term is just 1. It does not change with time. Okay? Alpha is 0. So this is what's called a center. So here centers, and a center is a fixed point which is circled by closed orbits, like we saw when we started our treatment of the Romeo and Juliet model. If you move away from this fixed point, you will start revolving in a closed orbit around it, with no growth and no decay, just in a circle. So here the whole phase plane is filled with closed orbits. And in the middle you have what we call a center. It's not, okay, the center is not strictly stable, right? It's not attracting, but it is Lyapunov stable. I still mark it with a closed circle, a filled circle. Okay. Before I go on, I like to add the drawings here. So, stable node. Unstable node. Unstable spiral. Stable spiral. and a center. Now, second special case, one of the lambda values is equal to 0, or lambda 2 equals 0. So this means delta equals 0. The trace can be positive or negative. So now we are on this axis here, the tau axis. And you can imagine that what happens here is that there is no growth and no decay on one of the eigendirections. And what we get is a line attractor if the remaining lambda is negative, or a line repeller if the remaining lambda is positive. So here we have line repeller, and here we have a line attractor. And we already saw these things. Okay, so a line repeller, say the x-axis is a repeller, and everything goes away from it on the y-axis, for example. It doesn't have to be on the y-axis. And a line attractor, then everything will go into it. So we have a line on which it's as if we have an infinite number of fixed points on a line, and each of these fixed points is, it's not attracting, but it is Lyapunov stable. But if you treat the line as a line, then that is attracting. If you go away from this line, you will go back to it. If you look at a fixed point on the line, if you go away from it on the eigendirection that has a 0 eigenvalue, you will not go back to your original point. You'll just stay there, because it's a whole line of fixed points.
And the line will be in the direction of for example, if
Yeah.
it's lambda 1, so the line will be in the direction of v1?
Yes. Lambda 1 is 0. Yeah. Okay, so the third case is when both lambda 1 and lambda 2 are 0. So we have delta equals 0, trace equals 0. Here. So this is a special case where we have a whole plane of fixed points. But it's a trivial case. So no growth, no decay on any direction. If you land on the phase plane, you just stay where you are. Okay. Okay. The fourth special case, lambda 1 equals lambda 2, but they are not equal. They are not equal to 0. So here we break this down into two cases. The first case is that we still have two independent eigenvectors. So they just happen to have the same eigenvalue, these two eigenvectors. So the growth or the decay on both eigendirections are equal in their magnitude. And what we have here is a star. We call this a star because its phase portrait looks like a star. It's not a spider shape like we had, but on every direction, in every point that you are on the phase plane, you just go straight into the fixed point. There's no curve because both eigendirections are equal in their magnitude of decay or of growth. So, and these cases occur on the parabola. Okay, because um, we know that the trace square over 4 is lambda 1 plus lambda 2 square over 4. This is just 2 lambda 1 over 4, and this is just lambda 1 square equals delta. So trace square over 4 is just delta. This is on the parabola star. But our second option is that we don't have two independent eigenvectors, but we have one eigenvector. So we just have lambda and v. AV equals lambda v. And what happens when we have a single eigenvector is the following. Say we have this eigendirection v, then any point in the phase plane is going along the eigendirection. And what we have looks like this. Okay, if lambda is negative, then we have everything eventually decaying along the eigendirection. And this is called a degenerate node.
Why is the decay circular enough?
Well, the way, just a moment, I'll just write it here. Degenerate node. This is a kind of let's see if I can show it. Okay, so I don't know how to show it here, but I'll need to think about it if I can demonstrate this.
Where on the parabola thing? So where is it that the stars stop and the degenerate nodes start?
It's not on the parabola. For the system that you got, you need to check whether you have two eigenvectors or one.
So they're both on the parabola?
Yeah, they're both on the parabola. Okay, so this plot that I made here is the most useful plot that we have in our course, and you will be consulting it for any system you analyze or any fixed point that you find, even in the nonlinear systems. And eventually, you'll probably know it by heart. It's not very complicated. Sorry. Okay. With what time we have left, I will start doing an example because I want you to see how I handle dynamical system that I'm given, and this will also help you solve questions on your exercise. And even if we don't manage to do the whole example today, then we'll see where we get. Okay, so we are given a system with this matrix. Okay, this means that the equations look like this. If we write it in matrix form, which you are asked to do in your exercise, have this. Of course, we can also write it in short, like this. Okay, so the first thing we should do about this, unless, as in the exercise, you're asked to take a different path, the first thing we do is find the trace of this matrix. Okay, this is -9, and the determinant. So this is -4 times -5, -2 times 3. And this is 20 -6, 14. So first of all, the determinant is positive. This is not a saddle. This is a node. The trace is negative, so it's stable. Okay. I like to make a small plot of the determinant versus trace and locate my system on this. So trace is -9. Determinant is 14. So I am in the quadrant that has stable nodes. Now, it might be a spiral, or it might be a regular node, or a star, or a degenerate node. I don't know yet. I want to remind you that what we are looking at is the properties of the fixed point at 0, 0. Okay? Any system like this has a fixed point at 0, 0. And we are looking at its properties. And we are saying that this is a stable a stable node, but we don't know if it's regular or a spiral. So next thing we do is we check trace square over 4 equals 81 over 4. This is 20 1/4. And this is larger than 14. Right? So the parabola that separates spirals from nodes is passing over here at 20 1/4, not at 4. Okay, not here. Here. Okay, so we have a regular node, a stable node. The next thing I do is find the eigenvalues. In the exercise, you are asked to find eigenvalues using the characteristic equation. I forgot to mention this term, but the characteristic equation is what you get when you do this thing, a minus lambda I. You take the determinant, and you get the lambda square minus okay. Lambda plus AD minus BC. This is the characteristic equation. So in the exercise, you are asked to derive the characteristic equation and then find the lambdas using the quadratic formula. But in some of the cases, you will already, you are instructed to already find the eigenvalues according to the equation that we found, which is lambda 1, 2, trace square minus 4 delta. Okay, so we have this. You can derive this anew. Or if you have the trace indeterminate, what we usually do is already take the trace indeterminate, put them here, and get the lambda 1 and lambda 2. Okay, so lambda 1, 2 equals minus 9 plus minus 81 minus 4 delta. This is 52. 81, this is 20, yeah, 29. Okay. Wait a minute, no, it's not 52, it's 56. Sorry. So square root of 25. So lambda 1 equals minus 4 over 2 equals minus 2. Lambda 2 is minus 14 over 2 is minus 7. So indeed, both the eigenvalues are negative, and this must be a stable node or a spiral. Oh, no, sorry, a node because they're real. Okay, I want to say that if you get a result, if this were different, and you would have gotten a result like this, square root, say, of 38. Okay? I want you to write the eigenvalues in this form, okay? Minus 9 plus square root of 38, or minus 9 minus square root of 38. Anything else is not correct, right? It's not exact. You may, after you reach this, you may approximate and then write minus 9 plus 6 over 2, and then go on, okay, minus 3 over 2. But this is the answer, okay, not something you got from the calculator. Then if you want to approximate in order to compare the eigenvalues and know the values later with the eigenvectors, you want to approximate in order to draw them on your plot, then you can use an approximation. But the correct answer for an eigenvector or eigenvalue will include a square root. That is an irrational number. Okay. So I do not have time to show how I calculate the eigenvectors. So I'll show that first thing next lesson. And so you can start with your exercise by already doing these stages for all the systems that you have there in question 1. And later do the calculation of the eigenvectors. כן.
יכול להיות ששתי דרכים לעשות אותו דבר, נכון? כן. אוקיי. לוודא כאילו, או מצאת העל שזה צבע מאוד ככה, והוא ייקח שתי צבע מאוד ככה. אז כן, שתי דרכים של בדיוק. אוקיי. וגם התרגילים חייבים לשאול אותם מלא. אני יכול לעשות עם עיפרון? כן, בסדר? כתבתי בהודעה שזה מומלץ לכתוב עם אס. לא, אפשר לכתוב עם עיפרון עם אס, אבל פשוט אני מוחק הרבה. ואם אני אעשה עם אס, יש מלא קשקושים. אז אם בסדר, אני אעשה משהו מיוחד. לא, לא. הפתרון הוא כמובן להעתיק מחדש להשאיר. אני יודע, אבל זה זמן. אין לי
תלוי איזה שלי יש.
סמך אחד.
מיטל כבר אמרה שהיא בורחת להורים שלי ברחובות.
טראומה.
כן.
סיפרת לי שאתה היית באילת. איפה זה שאני לא אבדוק שם? שהיה באמת רחב. אני לא יודעת אם לעשות מחר, אין תורן.
בעצם מה?
יש לי שיעור כל היום באחד. בדרך כלל אני לא מפסיקה בגלל שיש גם שעתיים.
כן, אז את יכולה לעשות, בואי, הבעיה היא שאני צריך לדעת, הבן שלי הולך לגן. אם הוא הולך לגן, אז מי יהיה שם? מתי יש אותו? אם הוא באמת הולך לגן, אז אני אהיה פה, ואם לא, אז אני צריך להגיע
המקסימום אני אעשה דברים אחרים.
כן, אני בטוח
אבל אני
שזה
כן
כאילו
תהיה להתחלה.
ברור.
מספיק בזמן וכל זה. לא, אז תגיד לי אפילו בבוקר. בכל מקרה.
בכל מקרה. אני אעשה עוד ניסיון.
ה-whole plane of FPS זה שהכל שווה ל-0
כן, זה בראשית.
וה-linear